Welcome back to Computer Science 3200. Today, here we are talking about bandit algorithms. Really the first algorithmic step on our journey towards arbitrary reinforcement learning. So let's jump right into it, shall we? All right, so lecture number 14 is talking a little bit more about exploitation versus exploration, and then we're going to talk about bandit algorithms, which are really the most basic form of learning that we're going to do in reinforcement learning. So we talked a little bit about exploitation versus exploration last time, and we said it was one of the main challenges in real life, and actually in the real world as well, is to manage the trade-off between exploitation and exploration. So in order to obtain lots of reward, our agents in reinforcement learning, they have to prefer actions that it thinks, at least, produce good results. But in order to learn which actions produce good results, it has to try them first. So whenever we're choosing to do an action, we have to balance that choice between trying something new in order to gain more knowledge or trying something we know in order to exploit its value. And this is also one of the main problems in real life. And I gave the example last time of something like going out to eat, right? So you've been around a little while, you've tried a couple of restaurants, and so maybe you have your current favorite restaurant. So the choice you would have in real life might be, do I go to the restaurant that I know is pretty good? Or this week, do we try a new restaurant that might be better, might be worse, might be the same, right? So sometimes you've got to risk a little bit. So in this case, you're risking your time, you're risking your money in order to gain some information. And that information is this thing a better choice next time you want to go out to eat? So learning. Learning is the process of gaining new knowledge or modifying existing knowledge, okay? So let me fix that slide real quick. I've got a bracket in the wrong place. Yeah, so gaining new knowledge or modifying existing knowledge. So we have learned something if we have information that we didn't have before, right? That's a pretty easy concept. Even if we're given the same results that we knew last time, like for example, if I thought something was good the last time or bad the last time, and then the next time I do it, it's good again or it's bad again, then essentially, even though I haven't gotten a new result, the result is still interesting because it makes me more certain about my previous result, right? So if I went to one restaurant once and the food was really good, I'm less certain about that outcome as a restaurant that I've gone to 100 times and the food was always good, right? So our estimates are going to have less variance if we keep getting the same results. So even if we don't get new information, meaning different information, we're still learning, we're still getting information. So let's look a bit more into exploitation. So exploitation is exploiting our current knowledge, choosing high-valued actions for which we already know the value, okay? And exploitation versus exploration is one of the questions that has appeared most on the exams, okay? So pay attention to this stuff. Exploitation is low risk because we're taking knowledge that we already have, but also possibly low reward because we know what we're going to get, right? So always choosing actions that we are familiar with gives us very little new information. And so we're getting rewards that we kind of know we'll get, but no bigger than that. But also no smaller than that, right? So it's low risk, low reward. Exploration, on the other hand, is trying actions that we haven't tried before. So not necessarily that we haven't tried before, but just that we've tried fewer times than other actions, right? In order to try and learn their values over time or become more certain of their values over time. So it's possible that new actions have higher rewards than actions that we've previously selected. And once we've explored sufficiently, we can exploit the best actions and truly know that they are the best actions, right? So let's say, if we had infinite time, then we could try all of our actions 1 billion times and get a pretty good estimate for which one is the best. And then we could choose that one from then on. So here is sort of the canonical example, the most intuitive example of this exploitation versus exploration problem, especially within the context of reinforcement learning. It's called the N-armed bandit problem. And it's called the N-armed bandit problem because slot machines, here we see like an octopus with a bunch of slot machines. A slot machine in Vegas has been known as the one-armed bandit, right? So it's one-armed because you pull the lever. Now they have buttons now. They don't have a big lever. Some of them still do. But you pull the lever, you pull the arm, and you possibly get some reward, right? And they're called bandits because they rob you of all their money. Like it's a losing venture to play a slot machine. So let's pretend that someone gave you $1,000 and put you in front of 8 slot machines and said, okay, how do you choose which slot machines to play, right? So the N-armed bandit problem is repeatedly making a choice among N different actions. After each of the actions that you choose, so in this slot machine case, you're choosing a slot machine, you're putting your dollar in and you're pulling the lever, and you might get some reward, you might not. So after each action, you receive a reward from a stationary probability distribution depending on the action that you chose. So what that means is that the reward that you get back from performing action A, one of the actions, is not necessarily going to be the same every time, right? Sometimes you might win, sometimes you might lose. So there is some probability distribution of the reward that you get for taking a given action. And your objective is to maximize your total expected reward over a number of action selections. So like we talked about last time, we want to maximize our expected total reward. So expected means on average, right? Because even if we've narrowed down the best slot machine, the one that gives us the most money over infinite time, it's not necessarily the case that that's going to give us the highest reward on the next pull, right? So it's the expected total reward over a number of action selections, okay? The N-armed bandit problem is also called the multi-armed bandit problem. And as I said, the name is an analogy to slot machines, the one-armed bandits. So you have a limited amount of money and you want to try to win as much as possible. And the thing is, how do we select which levers we want to pull, right? So the real world analogy here is just the same as the restaurant one. I've only got a finite amount of times to go eat. I've only got a finite amount of money. And so what I want to know is, do I eat at this restaurant next? Do I eat at a different one, etc.? So how would we how would we program a robot to learn which restaurant they would choose over time? So the multi-armed bandit problem is everywhere. We've got this sort of game show / real life decision. Do I take the new job, which might be better, or do I stay at my current job because I know how it is? Like maybe not me, but maybe me, but maybe you're frustrated with your current job, right? And you want to try something new, but that might require a move, it might not. I'm just joking. I love my job. But maybe there's another university that has more pay or cooler students or something like that, right? Or maybe there's a person you really like to work with at another place. And so you've got to decide, do you stay at your current job, which is all right, or do you go to a new one, which is which might be better, might be worse, might not be. So exploitation versus exploration again. If we can somehow maintain an estimate of action values, right? So at any given time, one of them has the highest estimate, right? That's called the greedy action. So if I've pulled 1 million slot machines and 1 million slot machine levers, and I've recorded all the different rewards over time, then one of them is going to have the highest value, right? And that's called the greedy action. So exploitation is choosing the greedy action, and that maximizes the single action returns over time. Exploration is choosing a non-greedy action to improve your action estimates. So that means that when you explore, you're not necessarily taking the greedy action. So you may forego some immediate reward in order to maximize future sum of or future expected rewards. Okay? So how do we balance that? That's important. So there's two important EVE concepts here. EVE, exploration versus exploitation. Number one is, how do we store and update the value estimates as we learn over time from new information that we get, right? So that's one of the parts of the algorithm, is how do we update our belief of what the action values are over time. The second part is, how do we choose which action to do next based on our current value estimate? So that's the second part. One is, how do we update our belief based on input data? And the second one is, based on my current data, how do I choose which action to do? And these are called action value methods, okay? Because you store the value of actions and then you take actions based on their values. So how are we going to store the current value estimates? Well, we're going to use this value called Q, okay? So we're going to have QT of A. So Q sub T of A is our estimate of the true value of action A after time step T. So here we've got Q star of A. Q star of A is the actual, like if we had an oracle that could tell us the actual value of this action, that's Q star of A. It's the actual value. The actual value meaning it's the mean reward or the average reward over infinite time steps. Okay? So as time t goes to infinity, we will estimate Q star of A. So Q is sort of the name. If you're talking in a programming sort of way, then you're going to have an array called Q. And you're going to have an index for each action where you're going to store the values over time. Okay? So how do we implement that Q value thing? Well, let's just take our example of the n-armed bandit problem. If we have some rewards, or if we have some actions, which are all the different bandits, so we've got a number of different bandits, okay? We've got Q of A, so it's some array indexed by the action, is the estimate of bandit A's reward. So choosing a bandit is essentially one action. So I choose slot machine 3 and pull the lever, that's an action, okay? So Q, for example, could be an array. There are other ways to store Q, but later in the course, we're going to be talking about that. So let's just use an array for the time being. So Q can be an array of size n for n bandits. So if we have 4 bandits, our Q array is going to have some values, right? So for example here, our Q at time 0, so remember Q sub t of A is the estimate of time t. So at the very beginning, that's Q0 before I've learned anything. So our Q0, and I'll get into this again in a bit, let's just, like our initial guess, maybe they're all 0, right? But then after some number of time steps, t, our Q sub t is going to look something like this, okay? So we've got some values after t time steps. So let's just look over that. Let's do a complete example so you know exactly what I'm talking about. Alrighty. So here's our example. In the top row, we've got our bandit actions, okay? So there's nothing behind me here. This is just bandit number 4. So we've got our bandit actions, 1, 2, 3, and 4. So you can think of, we have 4 slot machines, and if I choose action number 2, what I'm doing is I'm putting my dollar in, and I'm pulling slot machine number 2, and I get some reward out of that slot machine, okay? I'm going to record the rewards that I get from taking these actions in this area as I go on. And down here, I'm going to keep track of my Q values, so Q sub t of each action, okay? So Q sub t of 1 means after t time steps, so after t pulls, if t is 7, then I've pulled 7 levers. So Q sub 7 of 1 would be my estimate of the value of slot machine number 1 after I've pulled 7 slots, okay? Now, I've got one other thing here, which is if my keys will work, the distribution. So what does the distribution mean? Well, the distribution means how do I probabilistically get a reward from each of these slot machines, okay? So just because you have a bunch of different actions doesn't mean that all the actions have the same reward, right? In most cases in life, if you have different actions, they're all going to give you different rewards. However, instead of those rewards just being like 4 or 100 or whatever, they can have distributions. So here's a number of distributions that I'm going to use for this example. So slot machine number 1 is always going to give us 5. Okay, so every time we pull this slot machine, it's going to give us 5. That's the distribution. Slot machine number 2, whenever we pull that lever, we're going to get minus 20 or 20. Nothing else. So it's just an equiprobable chance of getting minus 20 or 20. When we pull slot machine number 3, we're going to get a random number between 0 and 10. And when we pull a slot machine number 4, we're going to get a random number between negative 10 and 10. Okay? Now, the person playing this game obviously doesn't know these distributions, okay? I'm just putting them there so I can generate the samples. So you can think of these distributions as like the source code inside the slot machine, right? Giving you rewards as you play. But the person playing this obviously doesn't know the reward, doesn't know the distribution, because you could mathematically analyze the distribution and say, you know, this one has the highest expected return, so just always pull that one. So I've listed the distribution here just for our example purposes. Now, the first thing that we have to do is think, how do I choose my initial Q values? So when I start the game, how do I know what my current beliefs are? Okay? Now, there's a few different ways to go about this, and it usually depends on the context of the problem. So for example here, if we're talking about winning and losing, betting money, possibly losing my bet, possibly gaining money, sometimes what you'll do is you'll just say, okay, let's assume at the start all zeros, okay? Because sometimes I can win, sometimes I can lose, and the average of winning and losing is 0, so we'll just say all of these are 0. But what you have to do is you have to give some initial value to all of these things. So Q, our array Q at time step 0, is just whatever value we give it. And in this case, I'm going to give it zeros because it sort of makes sense. Okay? So my guess overall is that neither of these bandits is advantageous and neither of these bandits is disadvantageous to me. They're all kind of neutral. Now, it turns out that that's not the case. So if we look here, let's do a little bit of analysis on these. So the first bandit is always going to give me 5. So what is the actual Q star for 1? Well, it's just 5. Because no matter how many times I pull that thing, it's always 5. So I know I'm going to get 5. But we're pretending we don't know for now. What is the expected value from bandit number 2? Well, if we always get either minus 20 or 20 with equal probability, then our value actually is 0. Right? Our average value over time is 0 from this. Here we have a random number between 0 and 10, so the average value of that would be 5. And over here we have a random number between negative 10 and positive 10, so the average number of that would actually be 0. Okay? So the fact that I've chosen some numbers to be the actual values at the beginning, that's just complete coincidence, and when I made up this example, I maybe wasn't thinking ahead, right? So that's how we're going to assign these. But if we have another problem, we may not want to have initial values of 0. Maybe we want to be really optimistic or really pessimistic to start, okay? Or maybe we want random values in here, who knows? But for the most part, if we don't know anything, let's just choose 0, okay? So now we're going to look at two different ways of estimating our values as we pull slot machines, okay? So there's two main variants that we're going to look at. One is called the sample average estimation, and the other is called an incremental update estimation. So the sample average estimation, as you can probably tell, we're going to average some samples, right? So let's look at that one first. So QT of A, sample average estimation. So the natural way of calculating QT of A is to average the rewards received so far after some number of plays, right? Seems pretty simple. So if at play T, meaning play T means the tth time that you've pulled a slot machine, if action A has been chosen KA times, yielding rewards R1, R2, all up to RKA, then just implement the formula for an average. Okay, so QT of A is equal to all the rewards that you got for performing action A divided by KA, which is the number of times that you pulled that lever, right? So it's really easy. It's just the number of times you've played that slot machine, okay? So you sum up all the rewards that you got and you divide it by the total number of plays. If KA is 0, then you're going to have like division by 0 here. So just define, like we did before, if KA is 0, just give Q0 some initial value, maybe 0, okay? As KA gets large, QT of A is going to converge to Q star of A. And what that means is, as you play more and more and more times, your estimate of the average gets closer and closer to the actual average, right? That's just like the law of large numbers or whatever they call it. So if we average the samples, we get the sample average method. Super easy peasy, right? Okay, let's just go through an example so you can see how this kind of works out and the good parts of that and the bad parts of that. So here what we're going to do is we're just going to pull levers left to right. Okay, we're not talking about action selection yet. So we're just going to do 2 passes left to right with our pulls. So if I choose this lever, if I choose slot machine number 1 right now as the first one, what am I going to get as the reward? Someone out there should be able to answer that question. Okay, someone right away says the correct answer, 5, right? I'm always going to get 5, so I'm going to get 5. So what I'm going to do is I'm going to take the sum of all the rewards, so that's 5, divided by the number of times I've chosen this slot machine, which is 1, and I get 5 for my average. And we notice here that we went from Q0 to Q1, right? And now, so when you go to actually implement this in your code, you're not going to have a bunch of different Q arrays. You're not going to have Q0, Q1, Q2, Q3. You're just going to have one array called Q, and Q1 means kind of the state of Q, or the values that are in Q after we've done this thing T times, right? So Q sub T, if we've done it 5 times, Q, that's just what the current values in the array after 5 pulls. So now we're going to pull the next one. And let's say, so we could have gotten -20, we could have gotten 20. Let's just say we got -20, right? So we're going to update -20 divided by 1 is equal to -20. Okay, so obviously for the first pull, our average is just going to be the value that we get, right? So here it could be any random number between 0 and 10. Let me just say 4. Average is 4. And this is any random number between -10 and 10. So let's say it was an 8. So we divide it by 1, which is 8. Someone asked, why am I dividing by 1? Well, what we're doing is we're summing up the rewards that we get for each different slot machine, okay? And we're dividing it by the number of times we've played that specific slot machine. So we're dividing by 1 because we've only played the slot machine once, okay? Someone, RT is always Q4. Expand on that question because I don't know what it means. All right. So Let's keep going now, and we're going to get more rewards. So we'll get the first reward. We'll pull slot machine 1 again. Okay. So if we pull slot machine 1 again, we're going to get 5 again. All right. So 5 and 5, you add them together, you get 10. You divide by 2 because we've played this machine twice, and you get 5. All right. We're going to play slot machine 2 again. Oh, look, we got a 20. How convenient. So we sum those up. We get 0 divided by 2 is 0. We play the next slot machine. Oh, we got a 0. How unlucky. So we add them together. We get 4. We divide by 2. We get 2. We play the last slot machine, and we get a -2. We add those together. We get 6. We divide by 2. We get 3. So after 8, so after t equals 8, just so happens that we've pulled everything twice, okay? After Q8, this is the state of our belief of the system. We believe that slot machine number 1 is the best. We believe that slot machine number 2 is the worst. We believe this last one is the second best, and we believe this one is third best, okay? As we have mathematically shown from the distributions, it turns out that slot machine 1 and 2 actually have equal values, right? Because over time, this one will start to produce 5 as an average, and this one will always be 5. Now, maybe I should have chosen different numbers. I'll update this for the future, so this is like 6 or something like that. But this one and this one are actually tied, but you can see after just a few estimates, we don't really have enough data yet. And even though this one, in reality, over time, is worse than this one, so far, we've just gotten unlucky with this one, and we think that it's worse than this one, okay? So this requires lots of samples. And as you sample over time, your average gets closer and closer to the real expected value, right? Okay, so that is the really simple sample average estimation, which I've listed up over here. So you keep track of the rewards that you got from every action, or every slot machine in this case. You sum those up, and you divide them by the total number of rewards. That's what the average is. That shouldn't be too hard to grasp. Now, let's go into the second one, which is a little bit more complicated, but equally as intuitive, I think, once you get past a little bit of math. So this is the incremental update estimation. So we're going to do a little bit of math here. Don't get too scared. Okay, let's see if I can remember all the math. But just recall, we're not doing the math yet, but in a couple of slides, that our estimate Q of t, so our estimate of the value of A after t time steps, is equal to the sum of all the rewards divided by the number of rewards for that action, right? The problem here is that we need to store all of those rewards. So this is fine if you've got 8 actions, but in simulations and video games and stuff, you're going to have billions and billions of samples, right? And you don't want to store billions and billions of data points if you don't have to. So the problem here is the memory and the computational requirements grow over time. So what we're going to do is we're going to figure out an incremental formula so that we no longer need that memory requirement, okay? So what we have right now is the following. We have that the new average is a function of the history of all the samples, right? So we need to record R1, R2, blah, 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 all the way up to RKA. And so that's bad. We don't want to have to record every reward we've ever gotten. What we want is for the new average to just be a function of the old average and a new sample. Okay? So can we keep a running average just based on the old value and the new value, but not have to keep all of those rewards? Okay, the answer, spoiler alert, we can. So here's the incremental average. Here's the formula that we have before, right? So Q sub K is equal to R1 plus R2 plus all the rewards, so the K rewards divided by K. So I'm not putting an action here. There's no A here. This is just the average or our estimate of the value after k time steps. Here I'm using k time steps because there's only one action in this example, is equal to the sum of the k rewards divided by k. That's just the formula for an average. Okay? Stay with me. We're going to take that formula and we're going to put it into the sigma summation term, right? And for anyone who's scared of math formulas, sigma summation is basically just a for loop, right? For I equals 1 to k, sum ri. That's what this says. So for I equals 1, so we have 1, 2, 3, all the way up to k. So for I equals 1 to k, you sum up r sub I. Take your it's exactly like a for loop. And then you divide that whole thing by k. So you got 1 over k on the outside. So let's figure out the formula if instead of we have k plus 1. Okay? So all we have to do is sub in k plus 1 for k. So we take this formula where we had q sub k, and we just have q sub k plus 1. So this is the average for the next time step, right? So this is 1 over k plus 1 times the sum of ri from I equals 1 to k plus 1. Literally all you do is you take this formula and you plug in k plus 1 for k. All right. Now we're going to do a little mathematical, we're going to be math magicians here, and we're going to manipulate this formula to our liking. So on the next step, what we do before, it used to be from I equals 1 to k plus 1. But we're going to change it from I equals 1 to k, and the way we do that is by pulling out that one last reward from k plus 1. See how that works? So if we have all the sum from 1 to k, that is this formula, which we had before, and we're just pulling out that final reward as an extra term. Okay? All right. Now what we're going to do is we're going to pull out the k. So why can we do this? All right? The reason is this formula here, this is a little bit of a tricky step. Let's look at this formula here. Okay, this part right here. Q sub k is equal to 1 over k with this summation, times this summation. Now, if we look, this part of the formula right here is identical, if I can circle that, this part of the formula is identical to this part, except this one was divided by k. So we have to multiply this by k to get that same term. All right? So if qk is equal to 1 over k times this, then k times qk is equal to this. So we can sub in k times qk here. All right? If you didn't get that the first time, just look it over. And so what we've done is we replaced this by k times qk. Now what we're going to do is we're going to do a trick that mathematicians love, which is adding and subtracting the same term. All right? Now, all we've done is we've added 0 to the equation, but we've introduced something really neat, which will allow us to do a trick in a second. So we've added qk. So we've just flipped this term and this term. Okay? Then we've added qk and subtracted qk. Well, why did we add 0 to this? Doesn't matter. Well, it's so that we could do a little trick with this one right here, which is we can take k times qk plus qk and sub out the qk and have k plus 1 outside of that. All right? So if we do that, then we have qk, which we can now take outside, and we have qk plus 1 is equal to qk, because this k times this qk, then divided by k plus 1, right? So this qk comes out, or this k plus 1 comes out because of the division here. So we have qk plus 1 over k plus 1 times rk plus 1 minus qk. So what in the hell does that mean? In English, it means that the next time step is equal to the average update for the next time step at k plus 1 is equal to the average at k plus 1 over k plus 1 times the next reward minus the previous value. So what we've done is we've eliminated the need to store all of this history, right? And what we have is exactly what we want. We have the update for the new estimate being a function of the old estimate and the new reward value. Okay. So if QK is the average of the first K rewards, right? And QK plus 1 is this form, which we just talked about, which is now, as we've derived, equal to QK plus 1 over K plus 1 times the new reward minus RK. What we have is the following. The new estimate, which is QK plus 1, is equal to the old estimate plus, which is equal to QK, right? That was the old estimate, plus some step size, which just happens to be 1 over K plus 1 here, times the new sample minus the old estimate. So we've just derived the formula for our desired new estimate, which is pretty cool. So the new sample is referred to as the target value. And I want to show you what all this means in practice, okay? So before I get to that example, actually, let me... Okay, so I got my slides a little bit out of order. That's okay. So what we've done is we previously had the average estimate relying on this possibly really large history of averages, and now we have our new estimate only relying on the old estimate, some step size parameter, which for the average is 1 over K plus 1, and the new sample, which is exactly what we want. Okay, I'm going to come back to this with an example that will show you exactly how this works. All right, but first, what if our distribution changes dramatically as we are carrying out our learning process? So what I mean here, instead of this always being 5, what if 2 million time steps in the future, this changes to always being 10? Okay, so for example, if we can think of like maybe a natural example, maybe we have a fire going, right? And so we have some heat value associated with being in this area because it's near a fire. What if the fire eventually goes out? Then being next to the fire doesn't have the same reward anymore, right? What if the food source in that area runs out? What if the stove is no longer on? What if there's no more candy in the dish, right? These distributions may change over time. And so the problem here is, well, we'll get to the problem. If the distributions remain the same forever, then the problem is called stationary, okay? So here, when we did our little example, these were stationary distributions. They did not change for the duration of our experiment. However, if the distributions are allowed to change over time, then that's called a non-stationary problem. So imagine having an average of 1 for 1 million time steps, and then all of a sudden it starts giving you a reward of 0 or 100, right? And if this happens, if you keep taking the average, then the average is going to be too slow, because you essentially have like 1 million samples at value 1. At some point it changes dramatically, and it's going to take another 1 million samples before your average really changes that much, right? So changing reward distributions can be hard, and it's typically why we don't use average updates in practice, okay? So for non-stationary problems, so averaging works for stationary rewards, but not if the distribution changes over time. So what we want to do, ideally, is because, you know, the universe changes, people change, things change. And so we want to wait more recent rewards as better or more trustworthy than older ones. Like the thing I did last year should not be as trustworthy a result as the thing I did 5 minutes ago, right? So what we can do in order to implement this, where we weight more recent rewards higher than previous rewards, is we can use a constant step size parameter in our update function. And that parameter is going to be between 0 and 1, okay? And that's called alpha. And I know that this sounds complicated right now, but it's going to be, as soon as I get to the actual example, I think it'll be really easy to understand. So we're going to have our new k plus 1 estimate of q equal to qk plus alpha times rk plus 1 minus qk. So essentially what's happening is our new estimate, our qk plus 1, is going to be pulled toward our target by this value of alpha, okay? So let's just do an example really quick. If our previous estimate was 50, okay, so our previous estimate was 50, if we have an alpha value of 1 and we have a new sample of 100, well, what's that going to do? If alpha is equal to 1, basically it means trust the new sample completely. So let's look at how the math works out on that. So if alpha is equal to 1, qk, right here, right, qk plus 1 is equal to this formula. So let's plug in these values into the formula. So qk plus 1 is equal to 50, right, because that was qk, plus alpha is equal to 1, times 100, right, which is the new sample, minus 50, which is equal to 50 plus 50, which is equal to 100. So if alpha is equal to 1, essentially what we're doing is we're going all the way toward the new sample. And let's say, for example, we had alpha equal to 0.5. What that's going to do is it's going to pull us half of the way toward the new sample. So if alpha is equal to 0.5, then qk plus 1 is going to be 50 plus alpha, which is 0.5, times 100 minus 50, which is equal to 75. So let me show you visually what this does. This is the mathematics, but visually I think it's a little bit easier. So here we have the same problem we did. We have qk is 50, alpha is 1, and our new sample is 100, right? So here on our little timeline, our little number line down here, we have our current estimate, which is 50. We have our new estimate, which is 100. Alpha is essentially how much do we trust the new sample. So if alpha is equal to 1, then we're going to trust all the way to the end of this red line, right? Our old estimate was here at qk. Our new sample was here at 100. If alpha's 1, it's saying shift our belief all the way to the new value, okay? And so our new estimate is going to be all the way over here at the new value. However, if alpha is equal to 0.5, then it's basically saying this is the value of alpha, right? So if alpha is 0.5, then we don't go all the way, we go half the way. So we would come right here, and half the way between 50 and 100 is 75. So essentially, you take the old estimate, you take the new sample, and alpha is just how much do you trust this new sample, okay? And that's all that it is. So what we're going to do now is we're going to do the same problem that we did before, but instead of using the average, we're going to use this incremental update with alpha equal to 0.5, okay? Oh, and it turns out that if alpha is not a fixed value, but you set alpha equal to 1 over k plus 1, then what you have is the average over time. So alpha, if it's a fixed value, you produce more trust in new samples. If it scales over time to be lower and lower, then you're essentially treating everything the same, okay? So we are looking at this case where we have a fixed value so that new samples are weighted higher than previous samples. So let's go through the same example that we did before. All right, so here, and I'll go through this kind of quickly because it's it should be, the math of this should be pretty easy. So if we get a sample of 5, right, and alpha is 0.5, we're going to trust the new sample half the way. So we take our old value, we put it toward the new value half the distance, okay? So we go from 0 to 5, if alpha is 0.5, we trust it half. So we pull our value estimate half the way, which is 2.5. If we got negative 20, half the way from 0 to negative 20 is negative 10. If we got 4, then half the way is 2. If we got 8, half the way is 4, right? And you can see here that if we kept getting 8s, more and more and more and more 8s, we would slowly actually believe that it's an 8, right? Because we get half the distance each time. Now when we get the next 5, we go half the way between our current estimate, which is 2.5, and 5, so we get 3.75. See how that works? Even though we got no new data, we got closer to the actual value, right? If we get a 20 now, well, I was at negative 10. I'm going to get a 20. There's a 30 difference between those two numbers, so I have to add 15 to my current estimate. So you can see here that now we are trusting the 20 more than we're trusting the negative 20. Why? Because the 20 came most recently. And so if our distributions change over time, what's happening is we're trusting the new distributions more than the old distributions. And so even though we got a minus 20 and a 20 and the average is in fact 0, we're trusting the new values a little bit more. At the next one, we get a value of 0. So if we got a value of 0 and our current estimate is 2, then we go halfway from 0 to 2, which is 1. And over here, we got a negative 2. So if we were at 4, it would take us 6 to get to negative 2, and so this is also 1. So this time, with this value update formula, we have 2 1s instead of this one being better than this one. Okay? So this is how your value estimates are going to differ over time, because here's what it is with the incremental update, and here's what it was with the average update. So you can see that here, like the average update was 5, now it's a little bit less. Here it was 0, now it's a little bit more, so they can change over time. All right? Action selection methods. Now that we have value estimates, how do we know? So far, we've just been pulling from left to right, but left to right is not necessarily the best thing we could do. How do we want to choose our actions? Well, one of the ways that we could select an action from our value estimate is just greedy selection. At any given time, we're going to choose a greedy action called A star, for which QT of A star is the maximum of all the QTs for all the A's. So this just says, go back here, look at the highest value, right? Look at the highest value and take the action that had the highest value. That's greedy action selection. This method always exploits current knowledge in order to maximize immediate reward. No sampling or exploration is ever done with the greedy action selection to determine better values to see if they may be better. So for example, if we used greedy action selection with our problem here, well, what would happen is we'd pull the first lever, because it's just the first lever. We'd get a value of 5, and then 5 is better than all the other ones. And so we'd say, okay, pull lever 1 again. Pull. 5. Oh, look, 5 is still better than all the other ones. So we'd just keep pulling action lever number 1. However, here's where our initial values start to matter, right? Because we set them to all 0. So if we're doing greedy action selection and we set all our values to 0, then if we get a greater than 0 value from a slot machine, we're going to keep pulling that one no matter what if we're doing greedy. However, if we had initially set everything to 20 here, and we pulled a 5, then this one would still be 20, and so we would pull this one over this one, right? And so by setting our action values really high initially, sort of an optimistic guess, then what happens is, in certain cases, it can help us with greedy action selection because we would be trying more different actions. But in practice, we don't want to use just pure greedy action selection because it's like we don't do any exploration, and we obviously need to get more information. So to add exploration, we're going to choose a random action with a small probability epsilon. In the limit, as the number of plays increases, each action will be sampled infinite times. So this guarantees that as our number of plays goes to infinity, our estimate is going to go toward the true value. Okay? In theory, this works, but in practice, it may take a very, very long time to converge. So here's what happens. With epsilon greedy selection, what we do is a random action is chosen with probability epsilon. So let's say a popular value for epsilon is 0.1, meaning 10%. So 10% of the time, we'll choose a random action. Okay? 1 minus epsilon of the time, we'll choose the greedy action. So this means I'm going to prefer the greedy action because it has the highest current estimate, but I'm not always going to do that. I'm going to do random things sometimes. So here's a graph of what can happen if you implement greedy action selection. I apologize for those of you who may be colorblind, but there's blue on the bottom, red is in the middle, and green is here on the top. Okay? So here we have the average reward over time, and this is just from some distribution, which I'm not going to get into. For blue, we have an epsilon of 0, meaning no random actions. Green, we have an epsilon of 0.1, meaning 10% of the time we take random actions. And in the red one, we have an epsilon of 0.01, meaning 1% of the time we take random actions. Now, for the first few pulls, if someone had a question, is it a random action between 2, 3, and 4, or between all of them? The random action is chosen between all of them. Okay? So when we hit our 10% in our random number generator, we could choose the greedy action still. All right? So that's a good question, and it may show up on an exam. Who knows? All right. So back here, we have the top line is 0.1, so 10% random. The red line is 1% random, and the blue line is no random. And what this means is that you can see here at the beginning, up until about right here, they're all kind of the same, right? However, the blue line stagnates pretty quickly if it's not choosing anything randomly, right? So we're just going to keep pulling that 5, that 5, that 5, that 5 over time. The 10% random action is quickly going to find us new values which may be higher than that initial 5s, right? Maybe we go find the other thing which is worth more. That's the 10% random one. However, the 1% random one, it's not exploring as much, so it learns more slowly. However, over time, it will be... So here's that trade-off, right? Is that with a higher epsilon value, you explore and learn more quickly, but in the end, what you do is you're choosing the wrong action just 10% of the time, right? Because you've explored more and learned quickly, but you're still choosing random actions quite frequently. Versus the person who explores 1% of the time learns much more slowly, but eventually, once they've learned all the values well enough, they're only exploring 1% of the time. So you're balancing how fast do you want to learn versus how well do you want to perform over time. This is another example here, which is instead of the average reward, how often do you pick the optimal action if you take each of these epsilons, right? So you can see here that, with the greedy selection, you're very lucky if you ever choose the optimal action. With 10%, which is this green line here, you're going to learn very quickly which is the optimal action. So let's say here we had 9 actions or something in this example. Then we're going to learn which of those 9 actions or those 10 actions is the optimal one, and we're going to start pulling that more and more often. But with epsilon greedy, we always are still going to be 10% of the time doing the wrong thing because we're doing random things 10% of the time. So it learns to do the right thing very quickly. However, the 0.1% thing or the 1% thing is going to learn over time and eventually surpass the 0.1% thing, right? Because eventually, once it learns what the best action is, it's only going to be pulling random levers 1% of the time. So there's a trade-off with epsilon greedy when it comes to learning speed versus eventual, you're still doing random actions. So what some people do is they take epsilon, they put it up high at first, and then they scale it down over time so that you learn really quickly, but over time you set your values. You don't explore as much over time. So your Bandit algorithm implementation then looks something like this. You choose a value update method, right? So do you want to do sample average? Do you want to use incremental update? Which one of those? You choose an action selection method. So for example, do you want to use greedy? Do you want to use epsilon greedy? Maybe there's other things that you could do. And then you repeat the following process. You choose an action to perform. You get the reward value from your bandit, and then you update your value from the action. Once you've updated your value, you go up to the top of this loop, you choose an action to perform, get the reward, update your value. And that's the whole Bandit algorithm. So here is how this is the pseudocode for the Bandit algorithm using the incremental average formula, that QK plus 1 formula, and epsilon greedy, okay? So here we're going to be passed in the bandits, for example. Our Q array is we are going to initialize an array of zeros equal to the number of bandits. So this is like just what we did in the example that I showed. We also have to keep track of how many times we pulled each lever, right? Because in order to get the average, we do need to keep track of like how many times we did each thing so we can divide properly. And that's initially also going to be 0. So while true, we're going to set an action parameter equal to null. If we're going to generate a random number between 0 and 1. If that's less than epsilon, then our action is a random action. Otherwise, our action is the action which maximizes the current Q value. So we look over all of our Q values, and we see which index has the highest value, and that's the greedy action selection. So this is all epsilon greedy is. It's 2 lines of code. If a random number between 0 and 1 is less than epsilon, choose a random action. Otherwise, choose the greedy action. Then you simulate your bandits. You say, I'm going to do this action, and you get a value from doing that action. You store that as the reward. You increment the number of times that you played that action. And now you use that implementation of the incremental update, and you say, QA is equal to the previous QA plus 1 divided by the number of times we pull that action times the new reward minus the previous value. Okay? So new value is old value plus 1 over K plus 1 times the new reward minus the old value. Okie doke. There's another way that we could select actions. This is a popular method these days called the upper confidence bound. So exploration is needed because there's uncertainty about the accuracy of value estimates, right? So greedy looks good now, but we're not sure if it's the best. If we could somehow be sure that it's the best, if we could have some confidence measure, then that would be really great. Epsilon greedy explores, but it explores randomly. So what we want to do, it would be better if we could select among the non-greedy actions that may be close to optimal, with some measure for how certain we are about their values. And this is what the UCB selection method does, is it does exploration, but it does exploration based on uncertainty rather than based on randomness, okay? So here is the here is the UCB algorithm up in the top. Let me move my ugly mug. So it's AT, that's the action that we're going to choose at time step T, is going to be the action which maximizes this formula. And that formula is our previous estimate of the value of A, right, plus some constant, which we'll talk about, times the square root of the natural log of the total number of time steps divided by nt of A, which is the number of times we've chosen that action. How in the hell does that work? Okay, let's look through it. LNT is the natural log of the total number of time steps. Okay, so the total number of pulls of all slot machines. NT of A is the number of times that action A was selected. C is a constant that's going to control the degree of exploration. As C goes higher, we explore more. If C is 0, we never explore. This will be greedy. Typically, what we're going to do is we're going to try all of our actions once to get some initial guess. Square root is the uncertainty of the value estimates for action A, right? So if you've done any statistics, you know about like standard deviation, and this has a square root involved. So the square root term is an uncertainty about that. The function calculates a sort of upper bound on the possible true value for action A. And the point here is in this following term. You're taking the total number of pulls and dividing it by the pulls for this action. And what that means is, as the ratio of pulls of this particular lever approaches the total pulls, your uncertainty goes down, right? So if the amount of times you've pulled a specific lever is high in comparison to the total number of pulls, you've got a fairly high confidence about that value. Like if we've pulled 1,000,000 times, let's say, and we've pulled action 1 like all but 10 of those times, so 999,990 times, but we've only pulled action 2 10 times, we are far more certain about the value of action 1 than the value of action 2. So what this algorithm would do, it was take that uncertainty and it would weight our choice of choosing that action higher if we've chosen this action less frequently. Okay? So when T increases, but not NT, uncertainty goes up. So that means as we pull other levers except this specific one, that means that relative to the other ones, our uncertainty of that specific one goes up. And as our uncertainty goes up, we want to pull that lever more. All right. So over time, the UCB can lead to better values. However, in practice, epsilon greedy will learn a bit faster, but UCB will produce the optimal value over time. Okay, so it's just another way that you can do that that's very interesting. So in the future, we're going to be seeing this Q of SA. So we know what Q of A is. That's our value estimate of doing action A. But what is Q of SA? So QA is the value of just doing action A. The value of a specific action will vary depending on the state it was issued at. For example, moving up is good if the goal is to the up of you, if you will, but it's not good if the goal is down. So moving up has a high value below the goal, but a low value above the goal. So Q of SA is just the value of doing an action at a particular state. Okay? And here's where this is going to matter. In assignment 5, you're going to have a situation like this. So here are our actions moving around in a grid, right? So our actions up, down, left, and right. So our actions, action 0 is going to be up, action 1 down, action 2 left, action 3 right. And you can think of each of these actions as being a slot machine, right? Where you're going to pull a lever, you're going to go up, and you're going to get some reward from that. And the reward of that is going to be based on whatever different things the environment implement. Maybe there's lava there, maybe there's not, right? Maybe there's hit points there, maybe there's not. So at each state, each action, if you look at it as a slot machine, then each of the states is going to hold their own QA. It's going to hold their own estimates of doing the actions at those states. So here, we're going to have, instead of just one big QA, we're going to have a Q array at each of the states. Okay? So this is Q of S0. That's the value of moving up at a given state S. Similarly, going down left and right. And we'll get more into that as we go forward. All right. Exam questions. Could be, but not limited to. We've got a bunch of formulas here that you should remember, right? You should be able to do some examples like I did in the slides. Exploitation versus exploration. Action selection methods. So greedy, epsilon greedy, UCB. What's the effect of epsilon as it goes up or down? And of course, the Bandit algorithm, right? So we covered a bunch of stuff in these slides. Alrighty. So, we just covered Bandit algorithms. We're going to talk next time about MDPs and a little bit of dynamic programming when it comes to reinforcement learning, but sort of in a hand-wavy way so that we know what it is. Okay, we're not going to go too far down into dynamic programming, so don't let that scare you off. It's actually quite a simple concept in reinforcement learning. And then next Tuesday, so a week from now, we have no lecture because it's Remembrance Day, so just remember that. All right, thank you all so much for tuning in, and I will see you in the next lecture.